Questions? Where's that guy?
Oh boy, I give you a question.
Where's that guy?
Oh, you just got there nobody here. Yes, her question, there's nobody in the room.
Yeah, he was belted in.
You know what I'm talking about?
Yep. Franklin County, did you have a question?
Yes, you did a very good job of covering many things about the different types of satellites, but what do you recommend for residential use that has the least maintenance and the most reliability?
Oh. Yeah, well, let's see. I don't know. You know, that's kind of a loaded question because there's not many machines that we can match up with our loads. So when our next exercise, we're going to do a simple sizing exercise, look at the machine, what's available to us, and then we may only have one or two or maybe three selections that we can take from. But we don't have much of a choice between a Ford and a Chevy or a Toyota and a Mazda and what have you. We're only maybe limited to maybe two choices, and we're going to take the lesser of two evils. But you know, in general, the machines that are out there have been out there for quite some time and have records, you know, proven records. And so before you buy anything, I would suggest go to installer, get references, size up a machine, and then ask to, 3, 4 machines like that they have installed, and then go talk to the homeowners. Before you even talk about money, go there, kick the tires, ask the questions. What kind of performance? What kind of wind speeds you got? What kind of service? What problems have you seen with this machine? Stuff like that. And when you look at the price difference between a 10 kilowatt ARE at $71,000 and the a 20 kilowatt Jake for $77,000, you can get double the performance with $6,000 more money outlay. But the headaches are going to be greater too. So knowing that stuff, now you're learning that stuff. The Briggies are good machines. The AREs are good machines. They're all good machines for their applications. Yeah, hell yeah. Yeah. Do your homework. Number one thing, do your homework, do your research, ask the questions. There's the Solar Home Tour is the first weekend in October, and your state has one also. So all these public homes are open to you on this one day for free. You can go to them, look at what people have, and ask the questions. So here's the one day, the first Saturday in October, where this is available to you. I would highly suggest that. What else?
What did you say it was, the first Saturday in October?
That's the Solar Home Tour. ACES is the organizer of it, American Solar Energy Society. Go to their website, American Solar Energy Society, aces.org. And it's the first weekend in October. On Friday is a commercial business tour as well. Other news, there's a small wind conference in Stevens Point, Wisconsin, which is June 16 and 17. And that's like $150 to get in, and food and all booze and all that's included. Stevens Point, Wisconsin. Stevens Point. Yeah, where they make Point beer. It's a steal. That's where, if you wanted to take out the North American residential wind community, that's where you'd be. And then, just so happens that a couple days after that, June 19, 2021, is the Energy Fair. We host that event. It costs like $10, $15 to get in the gate, and there's over 200 different educational workshops available. for free to people, and about 300 equipment vendors. So that's the place where you can kick the tires with the manufacturers. That is the Energy Fair. Custer, Wisconsin. 7 miles down the road.
Is this all on your website?
It's all on our website. Yep. Our website is THE-MREA.org. Also in our backyards, May 4th to the 7th is the American Wind Energy Association conference. It's a bit pricey, and it's more geared towards utility scale people, but now they have a small wind component as well. We kind of debated back and forth whether to go or not, but so we're going to go.
What's that to get into? Or is it just
No clue. How much? $1,200. Yeah, that's a bit pricey.
Yes.
And even one day, like 3 or 4.
Yeah, that's the
Mhm.
full conference, so
Yep.
1,200 if you want to go to the seminars, and that doesn't include the pre-conference seminar.
It's a bit pricey.
It doesn't include membership.
But, if you got a company that's going to send you, maybe worth it.
Clay, I've got it. The back over here. July 21st and 22nd is Wind, Indiana. They'll be at the Indianapolis Convention Center. It won't cost you $1,200, but it's a two-day event. There's a track for small wind. Last year was the first year, and we're anticipating about 500 to 600 people this year.
Excellent.
So
Right in your backyard.
absolutely. It'll be July the 21st and 22nd. You can go to the Indiana Office of Energy website to find the information about registering.
Excellent.
And Purdue, as well as our website at Purdue, will have a link to it as well.
Other questions?
There's another one coming up at the McCormick Place in Chicago. It's May 4th, all the wind. That's the biggest in the United States.
That's WIA. That's the American Wind Energy.
Yeah,
That's the big show.
yeah, that's the expensive one.
That's a $1,200 show. There was somebody that had a question about utility wind. Oh, look at that. Here's the deal. Germany's putting up as much wind and as much solar as possible, and they're going to always. Why? Because they don't have many resources left in Europe, in Germany, and so the base loads are being taken care of, coal-fired plants, and then they're adding to it with the renewables. So just an explosion of renewable energy activity there. And on a sunny, windy day, and by the way, they're in a latitude greater than ours. They're further north than us. They have worse weather than us. They have more cloudy days than us. On a sunny, windy day in Germany, they're a net exporter of electricity to other countries. They do that. They do that and want to do that because they've decided that's what we're going to do. And as a society, and if we could do that too if we wanted to. We just have to do it. It's more than just dollars and cents involved in this. You had a question?
I was just going to ask what the name of the happening was on July 21st and 22nd.
It's Wind, Indiana. It's like Wind, Indiana, and it's they're at the Indianapolis Convention Center.
Cool. What about those outlying areas, eh? Any questions off-site? Bueller? Anyone? Okay.
Explain real quick what you mean by wild electricity. Is this the fluctuation?
What's the definition of wild AC? So wild AC is going to have with the wind speeds, it's going to vary in voltage and frequency. We're locked in the United States, we're locked into 60 hertz. Canada is 50. And Canada is 50, right? Is it? Oh, okay. There's other places that are 50. Well, let's just say that. And we're going to
I have a question, Bartholomew County.
One sec. We're going to take that three-phase wild AC. We're going to invert it to utility-grade AC electricity, and we're going to operate in parameters. We have to fit in with these certain parameters. If it's out just a few percent, it'll drop out. The inverter drops out and disconnects from utility. and was talking to, what's her name? I was talking to Eric here. He deals with the endurance machine, and they have a place out in Salt Lake City where the utility is all over, and the utility is actually going out of the parameters and knocking their machine offline because it's outside the parameters that the machine can operate in. So the utility is actually putting out poor quality energy. And what you'll see coming off renewable energy inverters, it will be cleaner than the utility.
There's your inverter that's actually controlling all the fluctuations.
Yep. The inverter's masterminding that whole deal. Yep. Except with the endurance. Yep. Which is that motor, which is now a generator. That's locking into what the utility puts out. Synchronous motor. Yep. Okay, that offsite. You in the red.
Yes. Instead of getting a larger 10K wind generator, what about the possibility of using smaller units that are easier to maintain and stringing them together? Mm-hmm. And this way have a more reliable source, and one goes out, you have backups there?
There's a section that we won't cover. It's in the latter part of that presentation, that paperwork you have, comparing the installation of 2 wind machines versus 1 wind machine. And pound for pound, it's more expensive to install smaller wind machines, dollars per watt to install, than a larger wind machine is. You got 2 towers, double the conductors, you got the machine, you got footings. It's I don't think it's, if you're looking at economics, I don't think it's viable. Other questions?
We couldn't hear the question that was asked earlier there in your audience there. Could you repeat that?
In reference to the wild AC?
Yes.
What is wild AC was the question, and the answer is with the wind speed, there's going to be variations in voltage and frequency. Capiche?
Thank you.
Okay. Anything else? All right. We're going to do a simple sizing exercise. This is something that you can do tonight when you go home. First thing you're going to do is you're going to grab your electric bills, find your electric bills, 12 months of them, and you're going to add them all up. 12 months, add them all up, get a grand total. You're going to be looking for the kilowatt hour consumption that you did each month. It's going to be kWh. What if you can't find 12 months of utility bills? Well, call up your utility company and they'll email or send you copies of those numbers, all lined up. If you can get 2 years' time or 3 years' time, you can start looking at trends. What are the trends of my energy consumption? Who has a young family? How many kids you got? 2 kids. Boy and a girl, 2 boys, boy and a girl. Over time, what do you think your energy consumption is going to be? Go up, go down, stay the same?
Well, the girl is 5, but by the time she's 13, it'll probably go way up. No offense.
That's true. So we can look in the future and see what the trends are going to be. How many people have kids that are just about ready to leave home? What are your electrical trends going to be, probably? They're probably going to go down over time. So we can look into the future also and look at our consumption. What is the average annual consumption of a home in kilowatt hours? About 12,000, yep. And that number just bumped up again from the DOE came out with that number this summer. It used to be 8,760. Now it's up to 12,000 kilowatt hours per year. Why? We got more stuff. Bigger homes, more stuff. Plasma TV consumes the same amount of energy as a refrigerator. That's huge. That's a huge amount of energy, as we'll see. So as fossil fuel prices go up to heat our homes, what are we going to do? probably switch over to electrical heating as well. So, you know, we have to think ahead a little bit. So we're going to size a machine that's going to meet all of our annual needs in this exercise. So we're going to overproduce in the spring, winter, and fall, and we're going to underproduce in the summertime because we don't have much resources during that time. And so we're going to overproduce, rack up credits, and then we're going to buy those credits back. And the goal is to size a machine that's going to meet our needs on an annual basis. So at the end of the year, we don't owe them and they don't owe us, right? So you're going to scrounge around, get 12 months of electrical bills, add them all up, get a grand total. And these are electric bills from our office. So we have production on, we have some production during that time period. We have wind and solar. This is what we bought from the utility that year, about 12,000 kilowatt hours, or about the average needs of a home on an annual basis. So the folks on this site have that pink sheet. The sites, people off-site, you're going to be getting that pretty soon. It's on the way. So on that pink sheet, this is on the left-hand column here. That's all the machines that are available to us in the United States. There's a couple missing off of this chart versus the one that's floating around here. These are the machines. Across the top is the average annual wind speeds. We have 8, 9, 10, 11, 12, bloody blah. And say down the 10 column, these are the production numbers you should see off of these machines. Okay? So we're going to match up our consumption with production numbers. I checked around here. I looked on a couple websites and I confirmed it with one of the folks in this room. You could see or should see around 11 average annual wind speed of about 11 miles per hour in this area, this site, in general. We're not talking specifics, just general. So if we go down the 11 mile an hour wind speed column, we're going to find a number that's going to be close or near what we need for our loads. At my location, we'd use 10 miles an hour. Over time, we know we have as low as 9.8 and as high as 11.2 in my place, so we just pick 10. A little bit conservative. It's going to meet our needs on a bad year, overproduce on a good year. So we're going to err on the side of caution. So what was our needs? 12,000. Going down the 11 mile an hour column, what do you see? What's going to meet our needs? Well, we got the WT6000, which is the proven, which would be about 1,000 kilowatt hours a year less than we need. Or what else? The next closest one is the ARE 442. That's going to overproduce our needs. Which one do you want to go with? What would you like to go with? Okay, let's go with the ARE 442 because that fits with that. Okay, ARE 442. Flip the chart over, and that's now we're looking at the turnkey installed costs of those wind machines right here. That includes parts, labor, materials. You just write the check and they give you the keys. $71,000. And that'll meet your energy needs on an annual basis. All right? So you pick yourself up, dust yourself off, clean your pants out. So if you don't want to pay $71,000 a year, what are you going to do? And you want to meet all your electrical needs. Use less energy. If you don't want to pay $71,000, use less energy. You know? How can we use less energy and live the same lifestyle? Energy efficiency. So there are people out there who can come to your home. They're energy site assessors, wind site assessors, PV site assessors. They're going to come to your home, look at your loads, find out what your goals are, make energy efficiency recommendations, size out a system for you, bloody, bloody, blah. And those site assessors will tell you that, in general, you can reduce a home's energy consumption through energy efficiency, doing the same amount of work with less energy input, no lifestyle change. You can reduce your loads by 30 to 50% right off the top. And it makes far more sense to do energy efficiency measures for your home by looking at these three areas. Refrigeration, including AC, how you light your home, and how you heat your water. By looking at those three things, you can reduce your energy consumption and still have the same lifestyle. You're not living in the dark, you're not living in the cold. For example, my parents had 2 people live in that home. They have running lights, running water, lights, TV, DVD player, blah, 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 all this stuff. They consume 13,000 kilowatt hours per year, a little bit more than the average home. Oh, I did it again. And my friends live in an off-grid home. They have a 1,000 watt system, fixed array pointing south all day, every day. And that system will produce 1,300 kilowatt hours in 1 year's time. They have lights, running water, TV, DVD player, blah, 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 all the same stuff my parents have, but they consume 1,300 kilowatt hours in 1 year's time. What's the difference? Well, Terry and Roke live in a home that's energy efficient. My parents live in a home that's energy inefficient. So I looked at their energy bills, did the same exercise we just did, and priced out a system for them. And there's just no way you can't afford this. So what can you afford? Well, you can march yourself down at Frank's hardware store and get compact fluorescent bulbs. You can go over to the Appliance Mart and get yourself a refrigerator that's energy efficient, same size as what you have now, cools the beer, cools the food just like the old one did, but consumes far less energy. And that makes more sense than building any renewable energy system. That's where it's at. Energy efficiency. And managing the loads as well. In general, for every dollar you spend on energy efficiency, you're going to reduce the cost of the renewable energy system by $3 to $5. So if you spend $1,000 on energy efficiency measures, you're going to reduce the cost by $3,000 to $5,000 for the energy system. And it just doesn't make sense to build a renewable energy system for inefficient loads. Oh boy, there's something in the air here. This little exercise is to illustrate that point. So I work third shift, go home, eat dinner, like to go to bed and read a book before I go to sleep. Pull the shades down. And in my backyard, I have 4 25-watt PV panels sitting out back, powering up my 100-watt incandescent bulb. All right, that's what I need to read my book. All right, 4 25-watt panels, 1 100-watt incandescent bulb. So we have 90% of the energy going into this bulb is lost as heat. 10% is actually used as light. So it's like a heater that gives off some light. Across the street, my brother is a little bit smarter than I am. He works third shift also, likes to eat dinner, come home, eat dinner, read a book before he go to bed. But he has a 25-watt compact fluorescent bulb, which has the same lumens as my 100-watt incandescent bulb. So we're same amount of work, less energy input. So 90% of the energy that goes into this bulb is uses actual work, giving off light. 10% is lost as heat. But he only needs a 25-watt panel in his backyard to power up that light. Much different. Doing the same amount of work, less energy input. No lifestyle change. So let's look at the cost. So I looked at the AEE catalog, which is floating around here somewhere. And a 25-watt panel is $275. I need 4 of them, or $1,100 worth of system just to power up my light bulb. My brother across the street needs 1 panel to do the same amount of work, so he's going to spend $275 to do the same job. If you're paying that bill, which one would you like? You know. And PV, I use PV solar electric in this case because it's modular. If you want more energy, you just add on more panels. You can grow a system over time. Let's look at a refrigerator. This was not my parents' refrigerator, but a refrigerator we have downstairs in the basement of our office building that we use on occasion. How did I determine this number? This is what the refrigerator consumes. How did I determine that? Well, I went to my local renewable energy store and bought a kilowatt meter, plugged this for $35, and plugged this into the wall, plugged the device into this meter, and it gives you watt consumption, and then it gives, over time it gives you watt hour consumption. So I can look at any 110 device in the home and see what the consumption is, and then compare that to the charts. Is this inefficient or is this efficient? So I compared it to the charts, and so it's consuming 3.6 kilowatt hours a day. The same size refrigerator, looking at the charts, the Energy Star charts, and I can get a refrigerator doing the same thing, auto defrost, same size, upper freezer, lower refrigerator, same everything, which will consume 1.3 kilowatt hours per day. Now, if I have to build a system to power up just that refrigerator, it would look like this. I would convert, for the old one, I would convert the 3.6 kilowatt hours per day to watt hours, divided by my resource. My sun hours is 4. On average, we have 4 sun hours per day. You're a little bit more than us, like 4.5. So I would need, in my answers, divide 4 into 3,600. Answer is 900. I would need 900 watts of solar electric just to power up that refrigerator. Cost, well, install cost is $8 to $10 a watt. I chose 10. So $9,000 worth of PV just to power up that refrigerator. Let's power up the new refrigerator. 1,300 watt hours per day divided by the resource, $325 a watt, 325 watts times the installed cost, $3,250. Which would you rather have? It's far cheaper. It doesn't make sense to build renewable energy systems for inefficient loads. Doesn't make sense at all. If you want to get rid of your money, just give it to me. You know. And going down to Frank's Hardware, going down to the hardware store, going to the appliance store, you can do that right today. You don't have to wait around for anything. And it makes far more sense. Compact fluorescent bulbs, refrigerators, caulk, insulation is not sexy. Renewable energy is. Don't fall for that. The answers is in energy efficiency. That's where the real answers are. Reducing the loads. Greatest opportunity, refrigeration, water heating, and lighting. Phantom loads. The other part of the equation is managing these phantom loads. So when you have an electronic device like a TV, a stereo, computers, when you turn them off, they're actually bleeding energy yet. They're still consuming electricity. So how do you identify that? Well, you get out your trusty kilowatt meter that you got from your local renewable energy store. You can get them at Lowe's, you can get them at Menards, and various other places. They're very inexpensive. And I walked around our office building and identified some appliances that you have in your home. Stereo, DVD player, CD player, TV, computer, when it was off, was still consuming 21 watts, and cell phone charger. Is it safe to say that most or all of us have this or more plugged in to the walls of our home, 24 hours a day? Safe to say. So I plugged it into the kilowatt meter. All those devices added together consume 32 watts a day. Or 32 watts. We don't have time yet. 32 watts, that's nothing. So 32 watts times time, we have 768 watt hours per day, times 365 days a year, 280 kilowatt hours per year. There's more than 30 people in this room now. 30 people in this room, we would consume about the same amount of energy, almost as much energy as a home consumes in 1 year's time. That's pretty significant. Chad's gone. There was supposed to be like 120 people in this room, and then there's like another mob out off-site. That's a lot of energy. That's a tremendous amount of energy that we're not even using. It's just being consumed. And on a national level, that's billions and billions of dollars. So, do we need more energy production? No, we need more energy efficiency and managing these loads. So what's the solution to these phantom loads? Well, plug your electronic devices into a power strip. When you're not using them, turn it off. Or switched outlets. I heard Belkin has a remote-controlled power strip now. You plug your devices into it. It must be battery operated. Plug your electronic devices into it, and it has a remote for it. So there's solutions, or just simply unplug the appliance. And if you're off-grid, boy, managing those loads is critical to the survival of that system. Dan Shears, another author, write this down, Dan Shears, he is coming out with a book on wind energy for me and you to read. And he has just oodles of books out there. Well-known renewable energy author. It was supposed to be out this month. It's not out yet. Chiras, Dan Shears. Him and his boys built an off-grid home. He lives in Colorado. Has nice PV system, nice wind system, PV wind hybrid system, feeding into a battery pack, and out of the battery pack, DC battery pack, into an inverter which changes it over to usable AC electricity. So home gets built, move into the home, and a couple days after being in the home, the batteries are flat. And they're like, drag the generator out, charge up the battery packs, run a couple days, and then the battery pack's flat. And there's scratching of heads. Run the generator, power up the battery pack, and then it's dead a couple days later. And they're like, okay, we got a problem here. Well, they were turning off the lights when they weren't being used, this, that, and the other thing. But what was happening was these phantom loads were just parasiting the production, the parasiting off the battery pack, that it just would run the batteries flat. So energy efficiency in an off-grid situation, no connection to utility, you're your own utility, that's absolutely critical. Fuel switching. The old school thought would be so if you want to bring down your loads, your electrical loads, would be to shift some of these high consumptive loads like water heating, space heating, drying of clothes dryers and the sort, shifting them from electrical appliances to natural gas or LP, so that you can bring down your electrical loads. Now the new school of thought, with the cost of natural gas and LP going up, and I think we're in a time period where it's just a fluke that they went down this winter, where we're seeing a shift of appliances from natural gas and LP back to electrical. And in our climate, it's absolutely critical how we're going to heat our homes. How can we afford to heat our homes? I think we're going to have to go back to electrical heating, or a mix of electrical, fossil fuels, and biofuels, or something else. So, I don't know what the end product is going to be, but we're certainly going to use more electricity for heating of the homes. So I think we're going to see switching back to electrical devices for home heating, water heating, and space heating. Let's see, where are we going here? Airfoils. Any questions on the sizing of machines? So like the question was before, which machine would you pick, in reliability and cost and what have you? Well, if you want to match up a machine with your loads, you may only have one or two choices, and you're going to do your homework, ask the questions. Or you may be, and there's this middle section that's not even covered. So we're going to make a leap from 5 kilowatts up to 10 kilowatts, and there's nothing in between, Yeah.
Since you mentioned solar panels, can you give a clue as to how large panels are? Say that we experiment that 25 kilowatt. I'm just trying to get I have a sense of how big these wind turbines are.
Mm-hmm.
Do something equivalently with a solar panel. What would be the square footage?
Well, okay, going back to the energy efficiency.
Clay, can you repeat the question for the?
Can you use your microphone?
What would be an equivalent size solar panel that would be needed to go along with this energy efficiency PowerPoints that you have in your booklet?
What is the size of the panels in the energy efficiency? Oh, got it. I'm sorry. In general, you can figure that you need let's see. 10 watts per square foot in general. So, so a 20 watt panel would be about 2 square feet. 100 watts would be about, do the math, 10 by 10. Yeah, 100 square feet. Yeah. Or square. Mm-hmm. Does that answer? And that's a good general basis. About 10 watts per square foot. Any other questions? Mm-hmm?
One thing we didn't mention when we sized this is you can't go above 10 kilowatts in Indiana if you want to back into the grid. So
Mm-hmm.
you may not be able to choose a system that's going to power your house.
Yes. So the question or the comment is, looking at the sizing charts, some of those machines just aren't available to us in Indiana. Once we go above 10 kilowatts rated output, so the Jacobs 3120, the Integrity, the V1517, the PGEs can't have them, and still fall in net metering. That's correct. Yep, that's correct. And so maybe our loads would be greater than a 10 kilowatt machine could provide. There's possibilities of that. Yep. Anything else? Yes, sir.
Earlier, somebody asked about can you get around that 10 kilowatts by going with a hybrid battery backup and grid tied?
The short answer is no, but the long answer is kinda. You could rig up a system where you would take and have a PV wind hybrid system that could be greater than 10 kilowatts, battery-based system. How could you rig this? It would be feeding into the one battery pack. You'd operate off that battery pack, disconnect it from the utility, but then have a utility connection to back yourself up on occasion.
Well, the reason why I ask is I have a 5 kilowatt solar grid tied system already in place, and then that limits me to 5,000 watts of wind.
Yep.
Could you do a bigger system onto battery, or is that?
No.
No.
You wouldn't
Okay.
be able to do that.
Okay.
What you could do, there's a couple of things you could do. And I'm just throwing this out, and it depends on how big your pocketbook is. And congratulations, it's really cool that you got a 5 kilowatt system. You could take some of those loads off and separate them off the utility and run them on a battery-based system. And then you.
Separate circuits within
Yep, absolutely. That would require separate circuitry. Yep. So you could run a battery-based independent system, independent of the utility. Pick some circuits off, maybe big loads, like a refrigerator or what have you, and pumps. You could do that, yeah. But now you're building two different systems, and you're putting batteries in. When you put batteries into the system, you're losing about 50% of your efficiency. So if you don't need batteries, don't get batteries. It would be a difficult situation. Not impossible, but we're talking in generalities today.
There is another solution. You can buy a system that's 3 times the power you need, and then go with a wholesale version of the utility pricing, so that you actually are producing enough. You're producing way more than you need, but you're actually covering yourself in cost enough. But then that becomes also expensive. So.
Oh, sure, certainly, yep.
But there are other avenues that you can take.
Sure. And we were just talking to staying at retail rates. Yep, certainly.
Why can't the 10 kilowatt limitation be changed?
Oh, yeah, good question. Let me tell you some stories, okay, real quick. Here's some stories. The interconnection agreement with utilities in Wisconsin used to be about this thick. Each utility had their own interconnection agreement, and you had to have a law degree to understand it, and bloody blah. Now that through action of the Public Service Commission and citizens speak in their mind. Now it's down to the front and back of one page of paper. That's all there is to it. And also, those utilities are required to have a contact person, and one person, one phone number. They're the contact person, and they have so many business days to get back to you. So, what's another one? There's co-ops in Wisconsin. Lots of co-ops in Wisconsin. 3/4 of the land mass is co-ops, and no, they're not required under federal law to do net metering or anything, or allow you to do anything. But who's the owners of the co-ops? It's me and you. And so people started going to the meetings and started participating. They're like, hey, you know what? We want net metering. And now, guess what? One of the biggest dinosaur co-ops in Wisconsin now has net metering because people said that's what we want.
There's another way around that, too. Over there in Wanatah, Indiana, there's a guy that has a 20K Johnson up there. And our utilities, it depends on the utility company. You don't have to sign a net metering agreement for them to buy power back. They'll actually put a shunt in the meter where it won't spin backwards. That's the way you can get around with putting a bigger system in. And then there's a few people in our area that's done the same thing. So the power that they're producing more is going back to the utility, but they're not getting paid for it.
Yeah. Yeah. So now you have a really inefficient
way.
battery.
Right. But that's the way around it.
Mm-hmm. So there's different ways to skin a cat. For my money, I wouldn't do that. Next up, now we're going to talk about rotors. I'm sorry, we're going to talk about rotors right now. I didn't tell you about this up front. We're going to talk about rotors, system types, towers, foundations, wind resources, quality and quantity, siting, and then good, bad, and the ugly if we have some time. Rotors. There's two different kinds of rotors out there. There's a drag device, and then there's an airfoil. The drag device, that's the one we saw that in the picture of the Persian wind machine, 2,000 plus years old. Still using it today for different applications. Pumping water, irrigation, wind monitoring. The wind is going to hit one side of this rotor. The rotor is the three cups together. Don't pay attention to this. The three cups make up the rotor. Wind is going to push on one side of the rotor, pull the other half of the rotor through the wind. Push on one side of the rotor, push the other half through the wind, or pull it through the wind. So only at any given time, only half of the rotor is operating. And we're going to collect wind speed data with this machine. Works perfectly fine. With a drag device, we can only go as fast as the speed of the wind, and we can only get up to efficiencies of about 15%. So this is going to be a low speed, high torque application. And we're going to use that to, water pumping, same thing, drag device. So the wind is going to hit a blade or a sail and push it out of the way, run some sort of mechanical mechanism, and then the jack shaft. And then we're going to do work. Here we're just pushing the blades or the sails out of the way. This is a Savonius rotor machine. So we're going to take a 55-gallon drum, cut it in half, split, offset the halves, put it on a shaft, either vertical or horizontal, and the wind is just going to move that push the barrel out of the way, half the barrel out of the way, and drag the other half through the wind. And in this case, they're they're running a compressor, which is aerating this pond. I don't know do you guys have winter kill down here for fisheries? So they're aerating this pond so that they don't have winter kill, getting air into that water. Here's another one. I don't know what they're doing with this, but if you have extra wheelbarrows laying around, you can make this. Not sure what's going on there. Here's another one. This is Savonius rotors, those barrels that are cut in half and offset. And they are pumping water from one side of a cranberry bog over to the other side of the dike. Works perfectly fine. Small flow, high torque applications. Going to run most of the time pumping small amounts of water. Here's another device. This is third world technology. When I taught this class in Fort Wayne, there was a fellow in there from wherever we were. Can't even remember where we were. Oh, it was South Bend. He was in Africa, and they were building this type of system. And then at the base, they hooked it up with belts to a car alternator. and charged up a battery, and this battery would provide lighting for a few houses, DC lighting. Worked perfectly fine. And that's what they had. They have lots of barrels laying around, car alternators, and this works fine. Here, this is at the WEA conference, AWEA conference. Here's a Savonius rotor machine, and hooked up to a generator. Does it work? Yep, probably it generates electricity, but it's not going to generate electricity on the scale or at the cost compared to the horizontal or the machines that have an airfoil. And they have to. That's who they have to compete with. Air pumping again. So so it's good for the characteristics are slow speed, high torque, low technology applications. We can pump water, grind grain, data collection, developing countries, what have you. The rest of our discussion is going to be based upon the lift device or the airfoil, Bernoulli's principle. So we have this wing-shaped design. We have this wing-shaped design that's larger on the front bit and narrower at the tip. And so if we have two molecules, air molecules that meet this airfoil at the front part, the one on the bottom is going to travel in a straight line, and the one on the top is going to meet the face and travel a greater distance, but they have to meet up at the tail at the same time. So we have, this is going in one direction, flat across, this is going up and over, and we're having an acceleration of the molecules over the top. This spreads the air molecules further apart, so we have, in fact, a low pressure system on the top of the airfoil and a high pressure system on the bottom of the airfoil, which creates lift. So we have a lift device. So now we have a system where we're pulling the blade through the wind. It's not being pushed out of the way, it's being pulled through the wind. Any sailors in here? How does a sailboat work? Much on the same principles. We're pulling this boat. The sail is a big wing, and we're pulling the boat through the wind. It's not being, or through the water. It's not being pushed by the wind. Far more efficient. We're going to have higher speeds than the wind. We're going to be able to achieve higher speeds than the wind. We're going to have efficiencies close to 54%. Bett's law says we can only achieve up to, I think, 54.7 or something like that % efficiency on an airfoil. Anyone know? 59-ish. So we can achieve close to 100% efficiency. We can't get that, but close to. And we can do the same amount of work with a smaller swept area than a drag device. Parts of a blade. So this is a blade off the AWP. The blade has a thick root. This is where it bolts to the generator. Thickest part, this is where the greatest stresses are. We have a rounded leading edge and a narrow, sharp trailing edge, and the tip of the blade. So this is an airfoil, a true airfoil, and in order for this to be in operation, we need rotation, right? So we have no wind, and we have to get this into motion to get lift to take place. How do we get it into motion? Well, there's a scoop built into this, a drag device built into this rotor, into this blade. So as the wind comes in, hits the blade, pushes it out of the way, gets the motion going, then we start to get rotation, and as the blade starts to rotate, the work travels further out to the tip of the blade. So when it's in at working speed, the actual work is taking place at the tip of the blade. Everything else, all this other stuff is just holding it out into space. So the actual work is taking place right out here. So this is the AWP blade. Each blade has built into it a twist and taper to account for that deep scoop, which is, I don't know, like 15-degree angle at the blade root. And all the way out to the tip is about a half a degree pitch. So this is where the work is taking place. And if you sight down this blade on break time, you can see the twist and the taper that's built into this blade. So this is a wooden blade. Let's see. This is a wooden blade, laminated. I don't know what this is. Might be cedar or something. Laminated, put together as a plank, and then it went through a CNC router, carved the basic shape. And then the next step is to paint this all black, and then sand it down till all the black is gone. Then you have a finished blade. Then you would put an automotive quality paint on it or what have you. Besides this, the fiberglass blade from AWP. This is the original proven blade, recycled milk jugs, probably about 10 cents a copy. And the new one, the carbon fiber blade, probably $1 bazillion a copy. But very nice blade. What else? Here's another fiberglass blade with a styrofoam core. This is the old blade that came from this machine back in the day, and then they switched it over to two-blade system. This is off of a Berge 1000. So this is uniform from end to end in the shape of an airfoil, and it's pull-truded through a die, just like you would when you build a ladder. And then it's just chopped up into whatever lengths. Probably 2 cents a copy. Something that's going to be a problem for our wind machine that lives at 100, 120, 160 feet. Do we have bugs up there? Do we have dirt up there and grit? Yeah, that'll erode our blade. So built into the system is leading edge tape from the helicopter industry. So we're going to put this on there. That's going to sacrifice itself, save the blade, and we can easily replace the leading edge tape instead of a blade. Fran Cherney's machine, he has the 3120, which I'll talk about a little bit later. He didn't do any service work on his machine, and a small section of tape was missing. And over the years, the blade just eroded to the point where it looked like half a silver dollar was missing out from his blade. So did it affect the performance? Maybe a little bit, but more importantly, it threw the rotor out of balance. And so over the years, this wooden blade just eroded away. Here's an aluminum blade right here. This is a composite. This is off the Whisper. There's a lot of different wind machines and internet machines that use this type of blade. So you see this over and over again, used in different fashions. Metal blades, you don't see metal blades very much. Internet machines, you will. What happens with metal? You work it back and forth on these horizontal axis machines that work back and forth. Hardens up, fatigues, and then breaks. Not very popular. Fiberglass is popular. Wood, still popular. The Jakes still have a wooden blade. The big Jakes. And metal. 2 blades versus 3 blades. The most efficient rotor would have 1 blade on it. 1 blade on one side and then a counterweight. The Italians and NASA and DOE tested those, and they worked fine. But when in our climate, you get ice buildup, starts throwing the rotor out of balance. So not a good mix. There was a lot of 2-bladed machines up until just recently. A number of 2-bladed machines out there, and this is the crux of that configuration. When the blades are parallel to the tower, the machine is free to yaw. And when the blades are perpendicular to the tower, there's resistance to the yawing of the machine. So in turbulent conditions where the machine is hunting in the wind, you have the machine free to yaw, resistance, free to yaw, resistance. And so you're going to have this machine chattering on top of your tower. And that's called blade chatter. and it causes wear and fatigue on the blade roots and on the fasteners and fittings of the machine. So the compromise is to add on a third blade so that any one time there's only one blade perpendicular to the tower, less resistance to yawing. So less efficient, but less wear on the machine. So with one exception that I can think of, there's everything else is three-bladed. Questions? How about you guys out in out on Outwatch, in the offsite?
Tipton has a question.
Sure.
Go ahead, Craig.
Is ice an issue with the blades?
Oh, good question. We have, at our site, we have lots of fog in around February, January, February fog, and it'll ice up the blades. And when you'll get a thin coating of ice on the blades, and it destroys the airfoil, and it slows down the rotor, drags down the rotor, and not an issue. Does ice fling off the blades? Not very much. It doesn't go very far because it's so thin. I haven't seen blades ice slinging off. I have seen with our 3.6 kilowatt Jake a time where the rotor iced up. We had freezing rain, lots of coating of ice on the rotor, and it still turned, but the aerodynamics were destroyed, so it slowed down. But then the wind kicked up, and we had like 40-mile-an-hour wind, and the rotor took off, and the rotor was out of balance, and the machine was just bouncing around on top of the tower. And I almost had a small heart attack. And with that particular machine, the rotor and the tail fold up parallel, and to turn the machine on, you pull down on a cable and a winch, and the tail pulls against a spring, and it folds out, and the blades are perpendicular to the wind, so we're all good. But in order to shut that down, if the cable mechanism is iced up, you can't shut the machine down. So any time that it looks like we're going to have an ice storm, we just shut that machine down. So that if we have to shut it down, we can't shut it down. It's just an insurance policy. What else? Well, let's do offsite. What do you got on offsite? Anyone else? Okay. Here?
I'm going to have a wind farm near me, and I might have a wind turbine as close as a quarter of a mile. Would that affect my own wind turbine?
No, not in my head. Anyone know what the spacing is between machines? It has so many blade links, but I can't remember. 1,000 feet? Yeah, it has to do with blade links between machines, whether it be big ones or little ones. And it's, I don't think it's an issue. Oh. And that's for the big stuff, or based on ordinance on occasion. Other questions? Mm-hmm. Oh, we're going to get to that later on. Yep.
On the wooden blade, I noticed raised sections.
This is an unfinished blade. So this was a plank, was run through a CNC router, and those are just grooves. And so the next step it would be to paint it black. If you were doing this yourself, you would paint it black, and then sand it down so all the black is gone. And then you'd have a smooth finish. That's what you want. Yes?
Is there a problem with the height of a wind tower related to aircraft? Because we have crop dusters that would come over.
Mm-hmm. We'll get to that. That's coming up. Yep. And there's going to be a piece of paper you may have to file with the FAA. Yep.
We've got a question in Franklin County.
Yes.
Go ahead.
Have you had any complaints of people saying that the flickering images was causing a problem, the flickering of the blades?
We're talking small residential scale. That relates more towards utility scale in my head. There have been occasions, like once a year, when the sun lines up with the rotor, and the rotor lines up with a skylight in our office building where you have a flicker off the blade, that lasts about a minute or two. It's not an issue. With residential scale wind, not an issue. And, even with utility scale wind, I don't think there's any documentation of anyone that's gone crazy from it. But I don't know. It could be. I could be wrong. What else? There's a number of studies that have been done. Go ahead.
Question from LaPorte County: is there an emerging standard as far as design of a blade or composite material, the material that's used, or can that be custom designed for the specific application?
Oh yeah, everybody thinks that their blade is better than the other guys, So a manufacturer is going to stick with what they got. Proven took and remanufactured their blade, did a very nice job out of it, but you're going to pay for it. But everybody thinks that they have the better blade. C'est la vie, eh?
Isn't NREL working on a standard for distributed wind systems? NREL is working with a group of folks within the industry to develop a standard
For
just small wind generators.
Oh yeah, that's the Small Wind Certification Council. Yep.
Okay.
Yep. Is that what you're referring to?
As far as a standard, as far as quality standards and tension, strength, and those kind of things.
Oh, I don't know the answer to that question. But there is the Small Wind Certification Council, which would cover some of that in their reliability ratings and the sort. But anyone else know? NREL, National Renewable Energy Lab, out in Colorado, they do testing of wind machines and the sort. Good place for data collection. Yes, one more?
So are any of these units UL listed then, or are they not been tested UL?
Oh, I don't think there's been any listing of any machines. Oh, SkyStream is UL listed, yep.
SkyStream has, and the Windspire has. And actually, we have to take that UL rating to most of the utility companies. They will not let you enter grid tied unless you have that. So SkyStream does, and then Mariah Power, the vertical wind generator, does.
But the inverters that link up with the utility, those are UL listed. Yep, absolutely.
So you don't need your windmill to be UL listed as long as your inverter's UL listed?
Depends on where you're going. Depends on where you are, but for sure, absolutely for sure, the utility is going to want to see the inverter UL listed.
Yeah, they want to see that because just because you have a inverter that's UL listed doesn't mean that the wind generator is going to shut off. Because the requirements is that wind generator has to stop as soon as the power shuts off. So there has to be some type of mechanism, electrical or mechanical, to shut that thing down when the grid goes down. So that's what we're fighting with a lot of the utilities now.
When the power shuts down, you cut it off to the outside world so the guy doesn't get zapped on the pole. Right.
We'll cover that in the next section that's coming up. What was I going to? I was going to tell you something. Oh, in the state of Wisconsin, that UL listing has been an issue with wind machines because there's only a couple that are UL listed, and to get the state incentive money, you need UL listed equipment, and so they've been just letting that slide through, but there's only a couple that are listed UL wind machines. I don't know. Where's our insurance guy? Mm-hmm. Yeah.
Your homeowner's insurance won't cover you if you don't have UL devices.
Yeah. We lost our insurance guy. Is Endurance UL listed?
We don't have to. We're not inverter-based.
Oh, yeah, that's right. Yep.
We actually won't work.
Yep. Okay. We have to take a break, right? Guy in the back? Pardon? 2:15. Okay, we're going to take a break at 2:15. System types. Yes.
Can you tell me about the wind spire, how that works?
We'll get into that in a little bit.
Okay.
We have an airfoil rotor, just like these, wing shape, and that's but instead of being horizontal axis, it's a vertical axis machine coupled to a generator, and the generator is right here, and there's a blade off that machine right here.
And it's also scavenous.
A what?
It's a scavenous. It goes around. Go upwind, downwind.
Oh yeah, sure.
It's a drag device, but yet it has the airfoil. It's a hybrid of sorts. Like a hybrid?
Well, it's not hinged blades. It's not hinged blades. Let's talk about that on break time, eh? And this is the guy you want to talk to right over there in the green shirt. Raise your hand. Talk about it on break time? Okay. System types. There's going to be 3 types of systems out there. There's one you won't see very often. That's the standalone type, no connection to utility. The least expensive type, the simplest type, is the utility intertie without batteries. So we're going to have a machine sized for your needs, or what have you, generating what? What kind of electricity is coming off of it? 3-phase wild AC, in general. And we're going to go to some sort of power conditioning device, which is going to change that from 3-phase wild AC to usable AC electricity. In this case, this is a SMA Windy Boy. We're going to come off of that, plug into our breaker panel, power up our loads. Any excess energy is going to go through the utility, spin our meter backwards, rack up a credit, and store on the utility. Now, there's going to be times when we're not generating enough electricity to meet our needs, or we're not generating anything, and we're going to buy credits back from the utility, buy that electricity back. So there may be times when we're powering up our loads with renewables and the utility, sometimes just with the utility, sometimes with all the renewables. So our meter disc, the disc on our electric meter is going to spin forward, backwards, stop, spin forward, backwards, stop all day, every day. And at the end of the month, meter reader comes, reads the numbers off the meter, subtracts it from last month, and we owe them or they owe us. That's how it works. And the goal is at the end of the year, nobody owes anybody anything. This is a 2,500 watt proven on the ground on a tilt-up tower. We're doing maintenance on it. So this is up in the air, 126 feet, generating 3-phase wild AC. Comes down the tower in 3 conductors. Comes into the building. This is the balance of systems. Comes through this disconnect into this control box. Now here's where it gets dodgy. Okay, stick with me. This is a SMA Windy Boy inverter. This comes from the PV industry. So it's the PV generation of this is called the Sunny Boy, and it takes high voltage DC input and then converts it over to usable AC electricity. Well, up until about 5 years ago, we didn't have this. We always had to have batteries incorporated into the system, unless we had a Jacobs or a Big Bergie, which had an inverter matched for that machine. Prior to 5 years ago, we always had to have a battery pack and then an inverter. We always had to have batteries in the system. SMA took their Sunny Boy, opened up the parameters on it, and made it so that you could couple up a wind machine to their inverter, but it had to have DC input. What are we producing? AC. So we come through disconnect, power input into this control panel. We're going to run it through a rectifier, turn it over to DC electricity, high voltage DC, run into the inverter, which is going to convert it to usable AC electricity, comes out as usable AC electricity through our kilowatt hour meter, the one that we own. It just clocks up production. It tells us the health of the system. First line of troubleshooting. Goes up overhead into our breaker panel, lands on this breaker right there. That's where the renewable energy system meets the utility. So we're backfeeding that breaker, feeding the power into our home, into our office building. Excess energy goes out to utility and stores as a credit. This is Randy Block's system. Here's a 10 kilowatt Bergie coming to producing 3-phase wild AC, comes down the tower, into the building, into the basement on this pipe, into the inverter made for that machine. All right, Xantrax is the manufacturer. Comes out of there is usable AC through his kilowatt-hour meter. That's the one he owns. That's not utility. Goes up overhead into this breaker panel. That's it. So it's the machine, the inverter, breaker panel. Now the crux of this, now this is the simplest, least expensive type of system out there. But if the utility goes down, you're down. You have no physical connection to utility. You have no storage on site. So your $70,000 machine is a lawn ornament at this point. You have no access to the energy on that machine. It's just going to freewheel. Also, you could say that Randy Block's system is also a new age, a hybrid nouveau. So he's got also PV on the outside of the building, comes in as high voltage DC into the Sunny Boy, and out as usable AC into the breaker panel. So he has a system, he has lots of loads there. So he has a wind system, which is going to produce lots of energy for this fall, winter, and spring. Essentially nothing in the summertime. But he has a PV array powered up off this inverter that's going to produce tremendous amounts of energy during the summertime. This is Fran Cherney's machine. This is in Milladore, Wisconsin. There's essentially nothing between him and the Mississippi. It's just flat. You know, there's corn and a couple cows, and that's about it. This is a Carter-era Jacobs. It's actually like a 2315 or something like that. It's not a 20 kilowatt machine. On site, generating electricity comes down the tower's three-phase AC, wild AC, through this cabinet made for, this inverter is made for that machine, through his kilowatt-hour meter into the breaker panel. Here's a few stories on this machine. We run a maintenance and service course for 5 years now. This machine we've been maintaining for about 5 years now. Fran's maintenance regime was to, as he was walking out to milk the cows, look over and see the machine. As long as it was standing up and turning, that was his maintenance regime. One day, Fran went out to milk the cows, looked over to the machine. Oh, hey, wait, it's not there. And because he didn't do any maintenance on this machine, you have vibrations set up within the system. Vibrations back out bolts. Well, there's three-legged tower. There's 4 bolts on each leg, so 8 bolts backed out and dropped out of the pads, out of the foundation, and the wind tipped the machine over into some spruce trees. Didn't go down all the way. So he got Peter's crane to come out, and they pulled it back upright, welded the pads onto the foundation, and then put the bolts back in. Fast forward like maybe a decade or so, no maintenance again had been done on this machine, and we went there with students. Kerry Daycheck started climbing up the tower, and he's like, wait a minute, all these bolts are loose. So we spent an entire day retorquing all the bolts on the tower before we got to the wind machine. Then we got to the wind machine. To fix the real problem, there's a drive shaft that goes from the differential down to the alternator here, and that had fallen apart. There's U-joints in there just like a car. Those had worn out and need to be replaced about every other year. So we replaced that, did the oil change on there, and what else? And this is the machine where the leading edge tape was missing, and it eroded a hole in the blade. So we couldn't do anything with that. Next year came up, and it was the rotor would turn, but the alternator wouldn't turn. And the drive shaft was still in place. So what had happened was, here we have an input shaft with a pinion and a ring gear. And then I think there's another pinion down here that goes down to the drive shaft, down to the alternator. U-joint. This pinion head broke right there. So last year, we went over and we had disconnected. Here's where the alternator is. We disconnected the top 10 feet of tower, got a crane in, and as he was backing into place, the crane operator was backing into place, the crane disappeared into mud. We spent the next hour and a half pulling the crane out. Got him set up, pulled the machine off the top of the tower, came down, pulled the blades off. They came off real easy. Pulled the tail off. That worked fine. Pulled the gear head off. Fine. Put the new gear head on. And was ready to put it back up again. Just flew. Everything just went fine. But we had to get the governor, remember that governor, that big governor that synchronizes the pitch of the blades? We had to get that off the old head and put it on the new head. Should be a simple process. Put a gear puller on the governor, torqued it down, whacked it with a hammer, nothing. Put a little heat on there, nothing. 2 days later, we took it to a machine shop, put it in a 100-ton press. 70 tons later, the governor popped off, and we could put it on the new gear head. But what had happened? Remember when we were messing around with the power equation? P equals half the density air times swept area times velocity of wind cubed. Well, they messed around with the A part of that equation, all right? So it is still standard operating procedure. You can put longer blades on this machine and take it from like a 15 or a 17.5 up to a 20 kilowatt output by putting on longer blades because bigger swept area, and take advantage of the mediocre winds. Well, you can buy Kevlar blades for this machine to bump up the rotor size, and that's what they did. And what happened was they worked fine, but in high winds, those blades flex, and they come back and they clip the tower. And that's what happened. They clipped 3 blades right off that machine. Installer came back, put on new Kevlar blades, worked fine, worked great. High winds came up, flexed the blades, and they collided with the tower and clipped them right off. And then he put the old wooden blades back on, and it works fine. Well, what had happened, and I assume is what happened, is that holding this governor to the tapered shaft is a piece of key stock, 1/4 inch square. And that had sheared right off and cold welded itself around the shaft. Just incredible. How much energy does it take to do that? I don't know. Probably about 6 blades worth, I'd say. Just incredible. Anything that could happen to this machine happens to it. We took the blades down, refinished the blades, filled the holes in, fixed that big eroded part in the blade, and put new leading edge tape on, Rust-Oleum rehaul, rebuild on that, and it works fine. Now he's got essentially a new machine. Should last another couple decades. So we'll see what happens this summer. I couldn't even tell you. The gearhead changeout? I couldn't tell you. I have no clue. I didn't pay the bill. And most of all the labor was done by students. He just had to buy the parts. So he got away with, he probably has a little bit under $5,000 invested in it, with the gearhead, the crane. Crane had to come out twice, and they had to re-insulate and bake the alternator also. But, but that machine is Carter area, 1980s vintage, For the amount of abuse it's had, he got away pretty cheap, I would say. The next system where we have power available to us all the time, we're going to involve a battery pack. So we're going to generate electricity, 3-phase wild AC. We're going to rectify it over to DC, feed into a battery pack that's going to be sized for our needs when the power goes out, our emergency needs. That's not going to power up all of our needs, just things we need to have running all the time. That might be refrigeration, servers, life support, coffee pots are going to run off this battery pack, and it's going to be sized for the average power outage and the average duration. If you don't have if you have infrequent power outages, you may not need this. If you have loads that you need to run all the time, 24 hours a day, you may be committed to this type of system. These batteries are lead acid, the cheapest ones out there. Lead acid deep cycle batteries, something you'd see in a golf cart or a forklift or floor scrubber type situation. These are L16, so those are about 110 pounds a piece, about $300 each. Who has the AEE catalog? You can look that up real quick. Anyone have that catalog? And when you have batteries, you're going to have interaction with those batteries. Every 30 days, you're going to look at the fluid level. Every 60 to 90 days, you're going to do a controlled overcharge of the batteries, get the sulfates off the plates. And every year, you're going to take all the bus bars off, clean everything up, and put it back together again. Oh, and by the way, every time you charge the batteries, you're going to get hydrogen gas off of them. You have to vent that out of the building. So, and it's going to lower the efficiency of your system down to about 50%. So it's going to take about, the efficiency has gone from 95% down to 50% now. So you're going to need a larger system to make the same amount of power. Then we're going to have an inverter that's going to operate standalone with the battery pack and interact with the utility. So we're going to feed off the battery pack, maintain this at 100%, parasiting our production, running through the inverter, powering up the loads through the meter to the grid. Grid goes down, meter automatically disconnects from the utility, powers up off the battery pack, and you're up and fine. Your machine, your system is powering up your needs. Utility comes back up again. The inverter sees that the utility is up and reconnects with the utility, and you're up and running. It happens in milliseconds. But you're going to pay for that convenience. It's going to higher cost of the system. Mm-hmm.
I still got the same question. Why can't you do that without the batteries and cut off the backfeed into the utilities so that you don't have to shut down your windmill during power outages?
Could you repeat the question, please?
The question is, why can't you, with a batteryless system, still disconnect from the utility and power up your loads? It doesn't work that way. It doesn't work that way because, go ahead.
I was just going to say, we get this question quite a bit with our system because people want to be able to be off grid or be able to have it power because it's a generator when there's no power to your house. Well, the issue is that this turbine is going to create power, and if that power has no place to go via either your house or a battery pack or the grid, then it's got to go somewhere. And if it's hooked up to your house and you don't have every appliance on at that particular moment, in other words, if you're not consuming every bit of that energy, then you're going to blow something because
Right.
there's no place else for that energy to go.
Mm-hmm.
So you have to have it either go to a battery pack, or you have to have it go to the grid, or you have to basically hope that you have everything on in your house and you're not going to blow nothing.
Yeah, it has to be loaded down. And you're going to have variations in the wind speed, which is going to be variations in the power available. And you have to have something to absorb that energy, whether it be dissipated as heat or dissipated as heat for water heating or some sort of capacitors, or something to absorb that energy and then release it. It's not going to happen.
Clay, we just have a few minutes before break. So just as a heads up.
Yep, let's take the next system out there is a standalone system, and you're not going to see it. Just not going to see it. We have lots of energy in the spring, winter, and fall. Nothing in the summertime. I've never seen a system like this. Anyone seen a standalone? I've never seen one like this for wind. You're going to always have to you would always have to back this up with a generator. PV systems, yeah, you'll see standalone solar electric systems backed up with a generator because we don't have the solar resources in the wintertime. Up in my neck of the woods, you're going to have you're going to back up your off-grid systems are going to be backed up in November, February when we don't have a lot of sun. And I've been down to turning off the refrigerator, packing it full of the crisper drawers full of snow so I could get an extra 20 minutes of Xbox. And so I didn't have to get the generator out. Once you get the generator out, you have to get it started, you have to find the gas, and guaranteed the next day the sun is going to come out. All right. Let's take 2 questions, and we're going to take a break at 2:15. All right? 10 minutes. How about the offsite? You in the black. Anything? Any questions? Yeah.
Are there any maintenance-free battery options?
Well, there's no such thing as maintenance-free.
They make them for automobiles. I mean,
Yeah.
I mean, I understand you still have to clean the terminals, but I mean, they have sealed batteries for automobiles.
Yep. We just put a set of gel cell batteries on one of our wind systems, and we're learning how to live with them. Never had them before. Yeah, sure you can. And you don't have to deal with the hydrogen venting, and you can lay them on their sides and stack them up vertically and have a smaller footprint. I really like that part of it. But we're learning how to live with them also. Just deep cycle gel cells. Yep. We went to a 12 volt, so when we only have 4, we need a 48 volt system.
Optima makes them for automobiles.
Yep. And I don't know what the brand name of ours are, but it's the absolute minimum size just to make that operate. Mm-hmm.
I guess I don't understand the difference between a generator and a windmill. Why can you not use all the energy out of a generator and, just leave it running with no load on it and not a windmill?
The generator takes care of that internally.
There.
It's all built into the generator.
Well, then why don't the windmills have governors?
Oh wait, what are you saying is a windmill?
Well, I mean, these wind generators that we're talking about today, when he said you have to have a load on them, you couldn't have like a make before break switch that would drop out the power line connection and still allow your windmill to supply your house.
No, not going to happen.
But you could do that. But you can do that with a generator, say a propane or gas powered generator.
That's correct. Yep.
Why
Well, I don't know. Anyone want to take a stab at that? Well, yeah, cost is a huge factor. Yeah, yeah. This is out of the scope of this class. Anyone want to take a stab at that?
It's built into the design of the generator.
I have to think about that a little bit. Next question. I can't answer that off the top of my head.
Back on the battery thing, what did you say about the overcharging?
Oh, you're going to, every 60 days or so, you're going to control the overcharge of the battery pack, and it's going to bubble up the acids in there, and it's going to knock the sulfates off the plates. Give it a longer lifespan. It's through the charge controller, the charge regulation. So you're not going to just dump everything into the battery pack. It's going to be regulated. And there's a feature on there that's going to allow you to overcharge those batteries, whether from the renewables or from the utility side.
So that is in the charge controller.
That's correct. What?
The charge controller is responsible for telling us to do that.
Yes, sometimes that is built into the charge controller or the electronics, and sometimes you have to go poke a button, and sometimes what did I have to do? I had to throw a generator on to get, you're bringing the voltage up beyond the specs. Okay, so like a 24 volt system, you're going to run it at about 29 volts. So you're going to overcharge higher voltage, get it stirred up in there. And it sounds like it's bubbling away inside there.
But what if you say you'll never see a standalone system?
Oh, you could, but I've never seen one.
I mean, you can't do it for a cabin or something like remote.
Sure you could. Yeah, totally. Yeah, you could. But you're going to back it up with a gas generator or something.
Completely off grid.
Yeah, sure you could do it. I've never seen one though. I've just never seen one. Yeah, totally possible to do. Yep. Off-grid wind, yep, totally doable. I've never seen one. Off-grid PV, I've seen them, yep. I think it has to do with dollars per watt to install it. That's my hunch.
So the PV is cheaper per watt than the wind?
On the small side, yep, absolutely, yep. Yep. Infinitely smaller dollars per watt to install, yep. Smaller, yep. One more.
All of these have the batteries
Before the inverter.
Is that because of the DC? Because it seems like you want to use the batteries after
Right.
you've used all your energy that you
Seems like a no-brainer to me.
Repeat the question.
So the question was, in all the diagrams, the batteries have been before the inverter, so the priority is the batteries. And That's the systems we always had. The batteries were always the priority, and that was always the crux as well. Instead of the AC side being the priority, and then you're just trickle charging your batteries, which makes more sense to me. But that's the systems that we have. With the exception of the Sunny Boy Island, which I'm not sure, but the batteries might be secondary. I'm not sure. But I'm going to find out, though. Because we're going to replace that. We have a system like that, and I would like to get rid of it. We have an Outback system. Batteries are priority. That's the way it is. C'est la vie, eh? Okay, let's take a 5-minute break. 2:30.